us to carry on with our studies. Today, I want us to get deep into the study around programmable logic controllers and see how far we'll get regarding that. We probably, I hope that our introduction class is going to be today, and then maybe on Wednesday we start the actual programming. Now, before I get to programmable logic controllers, the PLCs, I just want to do something that is also quite important, just to give you an idea of the technologies that exist around automation. And so I want to discuss the industrial control systems. All right. So I just want to briefly discuss the industrial control systems before I move on to the PLCs in great detail. Now, one of the technologies that we fundamentally use for industrial automation, these technologies are called industrial control systems. So all the technologies that are deployed, because it's not just PLCs that exist in terms of trying to automate our industrial processes. So any technology that is used in the industry to ensure that automation is achieved is called an industrial control system. Actually, it's typically abbreviated as ICS, an industrial control system. Now, these technologies, they're definitely used widely, but they incorporate a number of control systems, and that includes software tools, and so we use them to manage and automate all the processes that you may think about. They can vary in terms of their complexity. They are small technologies, they are sort of like intermediate technologies, and then they are very complex or comprehensive technologies. So some of those include, in fact, the most complex or comprehensive technology that exists, so is called the SCADA system. I think I mentioned this briefly in the previous class. This is sort of like the most comprehensive. So you have the SCADA system, which is a very comprehensive ICS. It's an industrial control system. So SCADA system stands for supervisory control and data acquisition. Okay, so that's a SCADA system. It's a very, very complex industrial automation control system. So it uses a lot of things. It employs computers. It's used a lot in industry. Apart from computers, it employs graphical user interfaces. Apart from that, you have to include maybe network data communication, because these systems must be interconnected. So the SCADA system is one of those systems that are widely used to provide a very high level of automation and control and monitoring. So, by the way, that's why it's a SCADA system. It provides automation, it provides control, it provides monitoring of processes in the industry. Is the first type of industrial control system, the most comprehensive or the most complex one. Of course, the second one is the PLC, which we will be dealing with in a great detail. But remember, the SCADA system also encompasses PLCs. So like I told you, that industrial control systems are vary in terms of their complexity. There are very simple ones, and then there are very complex ones, and then there are those that are in between. So PLCs are also big, but they're not as big as SCADA systems, because SCADA systems even encompasses the PLCs. But the PLCs we'll discuss in a short while, so I don't want to get deep into it, but it also interconnects the different solutions that exist in the industry into a single network, so that you're able to control and monitor your machinery and your processes. The other one is what we call the DCS, distributed control systems. Distributed control systems. Remember, we are talking about the industrial control systems, those systems or technologies that exist in helping with automation in the industry. So the distributed control systems are also just like PLCs. They serve the same purpose like PLCs, and that the purpose is to control and monitor industrial processes or industrial equipment. The difference between distributed control systems and PLCs is such that PLCs are usually interconnected within a network in a centralized place. So, for example, if we go to the lab, we have a network of PLCs, but within the control labs itself. If you are working in an industry, for example, you might have a PLC that is connected within that building. It is centralized. So it's a network of computers and other control equipment that are being monitored and are being controlled within a centralized place. That is what PLCs do. Distributed control systems are not centralized. They work as PLCs, but they have connections that go beyond a central location. So instead of connecting your modules, your PLC modules to a specific central place, they're distributed throughout a system. Think of it, for example, a typical distributed control system is one where you have Kenya Pipeline Corporation, where they are sort of like transporting maybe oil from Mombasa to their depots in Nairobi. So in order to be able to control the flow or to control the system from Mombasa to Nairobi, they have connected PLCs and distributed them along stations all the way from Mombasa to Nairobi. So their PLC is not centralized, because they need to be able to see which pipes are functioning, at what rate is the liquid flowing all the way, and what stations do they need to store them in tanks, what are the levels of the oil in those tanks, where do they have leakages along the way, and so on and so forth. So in order to effectively control and monitor that process of transporting oil from Mombasa to Nairobi, they need to have PLCs that are distributed. So they have a distributed control system that allows the automation to be in a large scale. It's not as, so DCS is over a larger scale than PLCs, because PLCs are centralized to a location or within a network, but DCS or distributed control systems are not centralized. So they're distributed throughout the system, so that you are able to interface several computers and even several equipment and configure them, but over a wide range of systems and, of course, location. So it is something that's also very, very, very critical. So if you go to Kenya Pipeline Corporation, for example, they will not be, they will have PLCs, but they'll also have a distributed control system that allows them to sort of move away from a single centralized place. So I hope that's clear. The other type of industrial control automation, remember, we are talking about the technologies that exist today that we use in automation, that is in monitoring of systems and control of automated systems. And we are talking about them in terms of their sizes or in terms of their complexities. The most common one that I'm sure each one of us has encountered is the human machine interfaces. That's also an ICS. It's also an integrated. It's also an industrial control system. Human machine interface. Let me just machine interface. HMI. This is very, very common because a human machine interface is simply a component of industrial automation where you have a user interface, or what we typically as laymen call a dashboard, that allows the human to interact with the machine. So for example, your phone has a HMI, or your phone operates a human machine interface. Your computer operates a human machine interface. If you go to an ATM, it operates a human machine interface, because these are devices that allow machines to interact with humans. And it can also help in monitoring the status of processes. Okay, so this is widely used all over the place because machines have their language, and then humans have their language. So in order to be able to communicate, you need that human machine interface. It's like an interpreter between different speaking people. So it must be somebody who is able to link the two different entities to be able to communicate properly. I'll move on quickly now. The other one is the PIDs. I don't know whether you should, at final year students should be able to know what a proportional integral derivative is. So this is a PID controller. So this is proportional integral derivative controllers. So, ladies and gentlemen, you must know that, this is one of the most commonly used industrial control systems, a PID. That's why we study them in class. We study a proportional controller, a PI controller, a PD controller, and a PID controller. Yeah, so in fact, I think we even did this in fourth year. I think in fourth year, second semester, there's a lab regarding PID, design of a PID controller. So a PID or PID control is simply a way of driving a system towards a certain very specific position or a certain specific level as desired by the user, or as desired by the controller. So you're using you're programming these controllers to be able to use what we're calling the closed loop control feedback, so that you have an actual output as close to the target or as close to the set point as possible. So you have an output, a desired output. But because you're using systems that are interconnected, sometimes that output deviates from your target. So in order to make sure that the actual output doesn't really deviate far apart from the target or your set point, you need to use a PID controller. Okay, so these are usually used in industrial automation systems for continuously modulated control of crucial processes. So if you want to control the flow of a liquid somewhere, you want to control the pressure of some gas, you want to control the speed of a car, you want to control the temperature of a room, you need a PID controller, because then it will be comparing the actual output from the target output or the set point, and then it will always be trying to mitigate or keep them as close together using a feedback control, a feedback sensor. So that's important. So PID can also be considered as an automation system. Actually, it is an automation system. That's why we call it an industrial automation system. All right, we have others. You can study this later. I just want to finish now. It's this is programmable automation controllers. Programmable automation controllers. Programmable automation controllers. These are also just like PLCs. Like I said, DCS is like PLC, and the pack is also like PLCs. And the pack is usually comprising of like a couple of microprocessors, so that they increase the computing power, so that it allows multiple processes to be performed simultaneously. Okay, so and then we have discrete controllers. Discrete controllers. These are the simplest, they're the smallest type of controllers you can have, or the smallest kind of industrial automation devices that you can find. They're used for very, very basic operations or applications. Okay. If you need something like a switch, you'll use a discrete controller because all you need is an on-off control. If you need a timer, you'll need a discrete controller. That's a discrete controller. A thermostat, very, very simple control devices. So those miniature control devices for very simple applications fall under discrete controllers. So you can see, ladies and gentlemen, that in the industrial automation world, we have a lot of different types of controllers, and each one of them is applied based on the complexity of your operation, or sometimes also just based on the application that you want to achieve. So these are several of those. You can have more, but these are the most common ones. Of course, you'll meet SCADA systems very often. You'll meet PLCs very often. I've told you you'll meet DCS, because DCS is simply an upgraded PLC, really upgraded, but I mean the coverage is wider and it's not centralized. Of course, every device that we interact with that's digital these days has a HMI. So PIDs, we teach them in class because they are that important, especially for industries. So you can have a look at each one of these later at your own time. However, my intention is to discuss this in detail. So from the studies that we are going to have in the entire semester will just be around that, the programmable logic controllers. Okay. Now, what is a programmable logic controller? I will try and provide certain notes that I have, but you can also take certain notes because not everything that is mentioned here in class is translated as notes. So what is a PLC? What is a PLC? There are several definitions of what a PLC or a programmable logic controller is, but one thing that we must all agree on is, one, because it's a programmable device, so we can call it a computer. Number two, we know that we use it in industrial grade operations, so we can call it an industrial computer. So basically, a PLC is an industrial grade computer that we use for automation. What do we automate? We automate several processes. They can be electromechanical processes, such as you want to control certain machinery, or you want to control certain things on the factory assembly line. You want to use them on you know, these games, or when you go to the merry-go-round or amusement parks, you will find the use of PLCs. You want to use them for light fixtures, you know, you can use PLCs. So the key thing is that this is an industrial grade computer that is used for automation of processes, or of industrial processes. So there are key things. Industrial grade computer. Then the function is for automation. But we automate industrial processes. So whichever definition you provide, these 2 points must really come out clearly. The 2 points must really come out. There are very formal definitions that have been provided for PLCs, okay? Like there's a very famous, I think you get it in your notes, definition that a PLC is a digital electronic device. That's just a fancy way of saying it's a computer that uses programmable memory to store instructions and implement specific functions. Those functions should be things like logic functions or sequencing or timing or counting or arithmetic operations. So that's just a fancy way of saying we have an industrial grade computer that we use to automate industrial processes. Very simple. Now, because this is a computer, it is not the general purpose computer that we usually encounter. It is designed for several inputs and several outputs. And I told you, it is designed to be rugged. That is, to operate in very, very harsh environments. I told you those environments could be those of extreme heat, those of extreme cold. They could be very wet environments or very dry environments. There could be environments that consist of huge vibrations. There could be environments that have very high noise levels, electrical noise, and so on. So these devices are very rugged, or they are very tough in how they are designed and in how they operate, so that you can use them for any or to perform any specific task that you have, despite the environment that application is going to exist. One thing that is very important for us is that PLC is a newer technology. Previously, we used what we call relay controls, okay? So the previous technology that was replaced by PLC was relay systems, was relay or relay switches. So let me just say relay controls, okay? So in order to control these relays were simply, we used to call them contactors. If you read the book that I recommended, you will see pictures so that it gives you an illustration of exactly what we are talking about. So these relay switches, or what we commonly refer to as contactors, were simply switches that you have to move from one point to another, like you have to switch them. They're hardwired control systems. Hardwired meaning you have to really operate them manually, physically. They were very mechanical in nature. Okay, so that if, like, think of circuit diagrams, you had to draw a circuit diagram, you have the electrical components that you have to install, you have wirings that are going on there, so you needed electricians to do the wiring for any task that you wanted. And if you had an issue with your application, or if there was an error, then you had to, remove the wires and reconnect them and interchange them and so on. So troubleshooting was very physical. I mean, a very manual process. So because this was a very tedious process, and I told you, because these relays devices were very mechanical, so they consumed a lot of energy. They consumed a lot of space. They were bulky, and because they required cooling, because they dissipated a lot of heat. So and then troubleshooting was very manual. It was a very tedious process. So in order to replace this, then PLCs came about, okay? So that we didn't have to go through the tedious processes of dealing with relay devices. So that is how PLCs were brought about. So I will not go further into that. If you were interested in that older technology, you can have a look. But as for me, I would want to go into the PLCs and just discuss them. So I think I mentioned briefly in the previous class that PLCs offered certain advantages over the relay devices or the relay logic that existed before. And one is, with PLCs, we had increased reliability. You had increased reliability. Because you see, in the previous case where we were using relay logic, I tell you there's a lot of wiring, physical wiring that is involved. And so even when you want to move to another operation, you have to do another set of wiring. So even if you are in one room and you want to repeat the same application in the next room, you have to again rewire the whole system. But PLCs use programs. And so once you write the program once and you test it and it works, if you're moving to a different location, all you have to do is download it to a different PLC. So you could replicate the same program in several PLCs. Unlike in relay logic, where you have to redo the entire thing, you have to buy new switches, you have to do connection afresh every time you want to apply that kind of application. You had to use a new set of equipment, you had to wire them afresh. But with PLCs, because PLCs are simply programs, because this is a programmable logic controller, a computer system that is simply programmed. So once you have written that program to perform a certain automation process or a certain monitoring process, all you have to do is every time you want to use that same PLC, you download it to the next computer that you want to use, okay? Because all the logic of that PLC is stored in a certain memory. We look at the architecture in a short while. So again, with relay logics, you could see that if I were to do some wiring or connection or an electrical wiring in one room today, I might move to a different site and I make a mistake. So there would be some error. And then now I have to check again, what did I do wrong? But with PLCs, once you have written the program and tested it, you are going to simply download it elsewhere. So there's no chance of having a wiring error, so to speak, because PLCs don't really have a lot of wiring involved. The wiring we are talking about here is logic. Every time you think about PLCs, think about logic. It's not a physical wiring, okay? So there isn't much of an external wiring that is involved with PLCs. Of course, there's a little bit of wiring involved, but it is not as much as for relay logics, okay? So that's why relays were called hardwired, because the wiring was very extensive, okay? In PLCs, there's a little bit of hardwiring. You still have to connect a few devices, but it's not as intensive as it were with relay logics, okay? So PLCs provide a lot of reliability over relay logics. They're more flexible, so they provide more flexibility. Okay. Just, I've also mentioned this, you know, it's easier to even change a program than to change a whole setup of a physical electrical wiring, because then you'll have to redraw the wiring diagram, you have to purchase wires and do a fresh wiring. But with PLCs, it's easy to change a program from one form to another, okay? The cost is low, so let me say lower cost. The cheaper PLCs are cheaper compared to the previous relay controls. So you save a lot of money or cost in using PLCs. And they don't require, PLCs don't require a lot of components as relay logic, okay? Then the PLCs have a better communication capability. Communication capability. Okay? Because these are controllers that are computers. So they can communicate with one another. So each of these controllers can communicate with a computer equipment. and they can perform functions. That's why they're used in SCADA systems for supervisory control, data gathering, monitoring of devices. You know, you can upload and download programs. So all the uploading and the downloading is simply communication. So all that is important, or an important advantage that PLCs have over the typical relay logics that existed. The faster response time. Okay, because these devices, because we use them for automation purposes, we require them to communicate at very high speeds so that we can use them for real-time applications. We do not want a lag between the point you provide a command to the point the output is provided. You require a very short lag time. In fact, if there could be no lag time, the better. It's only that realistically that cannot work. But at least they need to operate at very high speed so that you can use them for real-time applications. Okay, you cannot achieve that with relay logic. And then, of course, there are so many advantages. Let me write a last one. They're easier to troubleshoot. Easier to troubleshoot. This I can attest to. That, you see, the PLCs, they have within them, or inherent in the PLC, they're built with diagnostic tools. And these diagnostic tools are able to override certain functions so that as a user, you're able to trace and correct where there's a software program, or a software problem, and even where there is a hardware problem. Okay, so you can find and fix those problems easily. You can even display the program on a HMI, on a monitor, for example, and watch even how the program runs. Just like when you're writing a code and then you hit execute or run, you can actually see how the code is running in real time. So they're easier to operate with. They're easier to troubleshoot because, like I told you, there's so many ways. And for those of you who might have used this troubleshooting component of the PLCs when you are in the lab, you could see that you can check. It can display to you and suggest areas where there is a problem with your software, and probably even if there's a problem with the hardware, you can quickly identify that. Okay. So there's so many other advantages. I am not going to dwell into that. I want to go into a very, very important part of the study, which is to first understand, now that we know what these PLCs are, and now that we see their advantages compared to the previous technology, which was relay switch based, what is the PLC made of? Like, what are the parts of the PLC? What is the architecture? If I open up a PLC device, what will I find? What are the components that comprise a PLC? Okay. Very important. Now, the PLC consists of several main components, but remember, this is a computer. So because it is a computer, you have the typical components of any computer. So let me start by probably just giving a typical block diagram of what the PLC would be like. This is just a block diagram to represent some of the components, the major components that are worth discussing here in class. Okay. So basically, there are about 4 or 5 components that we have with PLCs. The first one, in any device, any electronic device, you need a power supply. Very important. In any electronic device, a computer system, you need the brain, and the brain is called the CPU, the central processing unit. And the central processing unit usually has memory to store the registers or the program data, okay? Very important. And of course, you need a programming device. A programming device. This programming device must be communicating bilaterally, not unilaterally, bilaterally with the central processing unit. The power supply has a unilateral communication because it simply provides power in one direction to the CPU. That is it. But then the CPU needs to be connected to the inputs. So I could say this is the input. That's the input module. And of course, you've got the output module. So the output module connected, of course, to the CPU. The input is also connected to the CPU. Okay. Now, please note that these are the main components of the main components of any typical PLC. Now, the output here is usually connected to output load devices. So you usually have, like, remember, this is the output of the PLC, but they're physical devices that we call field devices, output load devices. Here we have input sensing devices. So this is where students usually confuse a lot of things. We said a PLC is a programmable logic controller. That tells you it is a software. It is not hardware. So the components that have listed here, the ones that are in the dotted, the ones that are dotted in that dotted block, are parts of a software. Programmable logic controller. The controller is programmable and it is logic based. So it is not hardwired. It is a physical device. But we humans operate physical devices. So there's got to be a combination of hardware and software. So what do we use to link the sensing devices, or what do we use to connect to the input of the PLC? We use our input sensing devices. The input sensing devices are now physical devices that we can use to connect to the software part of the PLC. So the input of the PLC are simply logic-based inputs. But the input sensing devices are physical devices. And those physical devices could be things like, mostly they are switches. So it could be a push button switch, I think you've seen a lot of these, a button where you just press and that's it. It could be a selector switch. Now, these are physical devices. Please note, these are now physical devices. They could be sensors. They could be a limited switch. Could be sensors. So please note, the input module, this module here, is used to interface, is a device that is used to interface with real physical devices, like the switches, like the sensors that I have mentioned. The output, we'll get back to that again so that the point sinks in. The output devices is, once your PLC has run the program, it provides an output, but that output is a logic output. So in order to transfer it to be a physical output that now actually actuates a device, so that a device can move or something can happen physically or in nature, or physical nature, we need output load devices. So to interface the output of the PLC to the physical output devices that we work with in real life, we need things like we need the load devices, and the load devices could be a lot of things. Those things could be things like a motor, so we can have a motor, meaning the PLC has provided the control output, which is a logic. That control output logic, in order for it to actuate a motor so that the motor starts running, there needs to be an output module. So the output module interfaces the PLC output with the physical output that we want to actually see, or that needs to be physical in nature. So it could be a motor, it could be a fan. So a fan is an actual output device that we need to know. But in order to connect it to a PLC, we need the output module. And the output module is a logic-based module within the PLC, because the PLC is a software. It is not a hardware. Okay, we learn more as we go along. You need things like lamps. So a lamp may go on. Okay, you can have a heater, for example, as an output. You can have things like a solenoid valve, so that maybe it opens and closes. You need things like a buzzer, so many output devices that we. Now, ladies and gentlemen, please note, and especially if you're reading the book by the one that I gave you on programmable logic controllers by Petruzella, it's very specific that these input sensing devices can also be referred to as field devices. These output load devices can also be referred to as field devices, because these are actual devices in the field. These are devices that you can touch. So please don't confuse between the input field devices with the input module of the PLC. So in order to interface the PLC to the input field devices, you need an input module. Similarly, to interface the output field devices, things like motors, lamps, heaters, in order to interface them to the PLC, you need an output module within the PLC. So the input and output modules of the PLC simply are interface devices with physical field devices that we operate. Hope that is very clear. Like I said, the book has very good illustrations. You can see the difference. Anyway, so now quickly, you can see that this is just like a computer. And so you have your power supply, you have your central processing unit that is connected to a memory device. You need a programming device so that you have outputs programmed into the device, and also instructions also being provided to the user. Then you need the interfaces, which is the input and output modules. So the power supply, for example, is typically for PLCs. I'm not writing this. I think I'll share some notes with your class rep later, trying to revise them. The power supply usually for PLCs is to provide you with a DC or AC power in order to operate the PLC. Now, remember, the power supply can be one of two. You have PLCs power supply. You can either provide a DC power or AC power. So those PLCs that have want to operate on DC, the typical range for DC is 24 volts. I think you must have noticed that. So let me just say 24 volts DC. Like the Siemens one that we have in the lab. But if the AC equivalent is, I think it's around 220 volts AC, not 240. I know that our typical connection or outlet that we have is 240 volts rated, but the PLC is operated around 220 volts AC and 24 volts DC. That's important. Of course, I can't explain much about power supply. You know what the significance of a power supply to an electronic device. What I must mention again is the input-output modules. Remember, the input-output modules are simply to convert logic inputs or outputs into physical actuation. So you need, you have a PLC, which is software, but then you have the hardware devices outside. So in order to link those two, you need the input-output modules. So the input-output modules are basically interfaces for input devices or interfaces for output devices. And we've listed them in our diagram here. So that should be very clear. And there are so many input and output devices. I can't list them all, but the more we study, the more we do examples, we'll meet different input and output devices, what we are actually calling the field devices. Sometimes when we say the field devices, remember, we are talking hardware. But when we are talking about the input module, we are actually talking about the interface itself. We'll see the symbols that represent the inputs and outputs of the PLC. So don't worry about that. Then, of course, you've got the central processing unit, which is the processor. CPU, of course, like any computer, we usually say this is usually the brain of the computer. In this case, it's the brain of the PLC. This is the command center. This is where intelligence is provided to command all the activities or to govern all the activities of the PLC. So, of course, it needs memory so that it can be able to store and retrieve data. That's why it's always connected to a memory device where you can store and retrieve data. But it is the command center. It is the brain of the whole thing. And then, like I said, you've got the programming device. The programming device. The programming device, ladies and gentlemen, is where you enter your desired program that will then determine the operation of the PLC or the sequence of the operation of the PLC. Okay, so this is the programming platform. The programming platform. So this is where we say the control logic, where control logic is written. Now, please remember, again, I cannot overemphasize this. PLCs are based on logic. They're not based on the textual commands or the commands that we usually have in the text-based programs like C or C++. These are logic-based commands. And we know that logic are zeros and ones, highs and lows, okay? We'll go deeper into that when we start programming, PLC programming. But remember, when we say here, you know, it's typical of any human being to confuse because we have studied computer architecture before, or the von Neumann architecture. And every time we see a programming device, our minds goes to things like C, C++, or even Java, or whatever. No. This is a different programming device. This is control logic based. Now, remember the programming device can be a handheld device. It can be a laptop. It can be a computer itself. That's a programming device. So just like, think about it. And if you've interacted with PLCs in the lab, that's why it's very, very important you do. Some of these things will be difficult to forget. How are you entering commands when you are talking, you're designing the traffic light for a four-way junction, okay? How are you entering commands into your PLC? Using a programming device. You're using a programming device. So this is where you have your keyboard, you put in your keyboard to provide the command. Now, the keyboard is a physical device, okay? But it is not part of the PLC. Remember, The keyboard is not part of the PLC. Even for a computer system, the keyboard is simply an input device, okay? But because you have to enter a command, that command goes into the programming device of the PLC. So the PLC here is a platform for entering control logic to the CPU of the PLC. That's what we are referring to as a programming device, okay? Now, there are several other components. They're not as they're not really important. They're not as they don't stand out as much as these 4 or 5. Actually, let me just say 5. As these 5 components. Okay, but all of these PLC's components and functions are centered around the controller, which is simply programmed for a specific task. Okay, so the PLC must be able to accurately interpret and convert the commands for the CPU. Then it will define a set of instructions and then provide outputs that are then used to control actuators. And those actuators are the ones that are connected to the factory floor, and therefore they perform certain operations. We'll look at an example of how a PLC performs a specific task. So before we do that, we need to understand the working of a PLC. How does a PLC work? Working of a PLC. I know at the onset, the introduction is a lot theoretical, but now when we start doing the programming, you will actually appreciate the significance of learning some of these theoretical aspects. So remember, we defined what a PLC is. We have looked at the advantages of using PLCs. We have looked at the internal structure of a PLC, how what is made up of the PLC. But then we now need to understand, how does it work? How does a PLC work? Now, in a nutshell, you can just say a PLC works based on what we call a scan cycle. Okay? So a PLC is based on a scan cycle. And because this is a cycle, from the word cycle, it means it doesn't end. It goes round and round and round. So it means it works by one, continuously or continually. Yeah, what is the word? Continually? The English word should be continually. It continually scans a program. And remember, this scanning is very fast. It's the first scan may be the first, because remember we say it's a cycle, so it goes round and round. So the first scan happens in milliseconds. It's very fast. Okay, but it is sequential. As much as it is going is a cycle, there is a sequence. It's sequential, so let me just say it's sequential and repetitive. Okay, it is sequential and repetitive. So the scan cycle that we are talking about here is basically 3 main, because we've said the PLC is based on a scan cycle. That means it needs to continually scan a program, but it must follow a certain sequence and repeat that sequence. So the first sequence is called what we call the read sequence. The read, some book might call it check. And what do you read? Of course, you read the inputs. Meaning, if somebody programs the PLC to perform a certain task, the first thing the PLC will do is to scan and check for inputs, or what we call the input status. Meaning, is there a command that has come in? let us check if there are certain instructions that have been sent. Okay, that is usually the first thing. The moment it receives those instructions from the input by reading, what does it do? It executes the program or the instruction that has been read. So PLCs work on three main sequences. You read, you execute, and then you update the output status. Okay, so please note, usually the PLC has the input, then there is the execution of the instruction, and then there is the output. At any given time, even before you program the PLC, there is an input. The input could be null. There's nothing at the input. Then there is also an output. The output could also be null. It could be something, it could be an instruction, or it could be nothing. It could be empty for that matter, meaning there's no logic at the output or there's no logic at the input. But when you switch on your PLC, the first thing is it needs to check the input. So it will read whatever instruction exists at the input. The moment it receives instructions at the input, it executes those instructions. And once it has executed those instructions, then it does what is called an update. It updates the output. And once that is complete, that is known as one scan cycle. Then it repeats the whole process. So, and this is done in milliseconds. So it takes maybe 1 millisecond to read the input, execute the program, and update the output. That is one scan cycle. And then within 1 millisecond, it's gone back again to check the input. And if the instructions, it will execute, and then it will update the output. So basically, we usually say that we have three main sequence steps: read, execute, and then we have update. Remember, it's update output. You're not updating anything else. So because this is cyclic, meaning it's a process that goes like that. Some book can, you don't have to write it like this. Sometimes you can just say it consists of 3 steps, you know, as long as it's cyclic in nature, you know. So there's read, execute, and then update, you know. That's still the same process. But now we have to know that all PLCs, whatever they do, they operate on this scan cycle. This is how PLCs work. Check the input status, execute the program that exists there, and then update the output status and repeat it very fast. And that is how we achieve automation. Now, it's very critical for me to mention at this point that these are the 3 main operations of a PLC, the sequence of operations of a PLC. The 3 main ones. There are newer PLCs or manufacturers who've introduced certain stages within the scan cycle. And that stage could be considered a 4th stage. And so maybe after the update, they've introduced another stage after update, and that stage is simply for what we call troubleshooting and diagnostics. So this is troubleshoot. So you can see that troubleshooting doesn't occur every time. Troubleshooting is usually used whenever there's a fault, whenever there's an error. So we don't normally include troubleshooting as part of the scan cycle because we are referring to steps that must be executed or steps that must be followed during every operation of the PLC. And they are usually to read instructions, to execute the program and to update the output status. However, because I told you that manufacturers have introduced diagnostics within their PLCs, it makes sense that they would introduce it as part of the scan cycle, such that whenever there is an error within the PLC, or such that whenever there is a fault, you could now go to the step of troubleshooting. But remember, troubleshooting is only used whenever an error occurs, okay? So it's not something that you want to introduce as part of your normal operation of the PLC. It will be consuming time, and it would be consuming energy for no reason, okay? So at this point for our study, I want us to restrict ourselves to the 3-step operation of the PLC, where you read instructions, you execute the program, and then you update the output status. I'm emphasizing this because I know some people will read the book by Petruzella and they'll see a 4th stage or a 4th step in the scan cycle that has been introduced, and it's called diagnostics and communication. Now, like I've told you, you don't have to diagnose your processes during scan cycle when there is no fault. So we'll stick to the 3-stage scan cycle, where you have to read, execute, and update. But we must know as engineers that technologies advance, and usually they come with advancement even in the way the structure of the PLC is. And so diagnostics and communication is introduced as an integral part of a PLC operation, but it is not until there is an error or until there is a fault. Hope that is very, very clear. All right, so I've spoken a lot for about an hour to introduce just the PLCs and how the PLCs operate. But we are building, remember, we are building this knowledge into how we can start to program a PLC and see exactly how the PLC operates in solving real life problems. So I told you that you bear with me so that we just do a lot of this theory and understand most of the concepts around it, so that when we start doing the actual PLC operations, then we'll be able to understand a lot of the things that happen, okay? Now, we have talked about the PLC itself, but the PLC consists of 2 main things. Remember, we want to go into how can we program a PLC. So, because we are studying the PLCs, we need to first know what is the language that is used with the PLC. You probably might know that already. And then the programming. So we'll need to understand what we call ladder logic. And then once we understand the ladder logic, then we'll strictly now go to the programming aspect of the PLC. So we still just need to understand what is the language that PLCs use, so that now when we start programming, we know the language that we are programming in, and now we can appropriately program PLCs to perform certain specific operations. So I am tempted to introduce, because I want to do this in the next maybe 40 minutes and then I let you go, because we need to go into programming in details. But before we do that, there are certain specific things that I need to mention, again, which are very theoretical, but very, very important in guiding us towards programming, as it were. So before we get to this, probably we'll do this in the next class. I want us to just look at the ladder logic. So let me just say, let me call this the PLC, let me just call it ladder logic basics. I'm just introducing the very basic aspects of ladder logic. Then we'll go into the programming in details in the next class. We've defined what PLCs are. So what is a ladder logic? We have just mentioned here that a ladder logic is simply a programming language. So this is a programming language. I'm still just discussing the basics around it. I'm not going into the language itself. So a programming language used to program PLCs. Okay? Remember, this language is very graphical in nature. It's not text-based. It's a graphical language. And for those of you who've interacted with PLCs before, you can see it's simply based on symbols. Okay? Based on symbols. Okay? But these symbols, their work is simply to express logic operations. The symbols express logic operations, nothing else. Now, we are usually tempted to imagine that PLCs operate much like we operate with other programming languages. These symbols that we are going to look at simply transfer logic from the input to the output, nothing else. So this is a very fast and simple way of creating logic expressions in PLCs so that we are able to automate repetitive processes or repetitive tasks. Remember, this is why we brought in PLCs, that there are those tasks that can be very repetitive and usually time consuming and labor intensive, and human beings would get tired and they would not do them at the right speed or with the right efficiency and, with the right quality as the output. So usually it is important for us to introduce PLCs. So I want us to remember we came from relay logic. Relay logic was used with relay devices, but now we are using ladder logic. Okay? Before I look at these symbols that we are talking about that express logic operations, a few other things that I need to mention. Again, any engineer or any technical person can be able to draw parallels between an electrical schematic or an electrical diagram and a ladder logic diagram. You should be able to compare and know the differences. One thing stands out, that compared to the text-based programming languages that we have, the C, C++, C#, whatever, Java, whatever, Python and stuff, ladder logic programming is a lot easier, way, way, way easier to use. That's why it's very, very easy to even learn it on your own. And you can learn from several logic that is used by several manufacturers because the principle is the same. But you will notice that unlike the text-based programming, when you're programming with ladder logic in PLCs, you have the graphic symbols. You'll have to drag and drop them into a ladder diagram that simply is your code. So your code is like a diagram that resembles a ladder, and it comprises of symbols that are dragged and dropped into that ladder diagram. And it's a very easy program because even when you make mistakes while you're coding, quote unquote, meaning while you're dragging and dropping your symbols, you can quickly troubleshoot or easily troubleshoot, and you can visually see the flow of logic from your ladder diagram. And we look at the components of the ladder diagram so that we have a clearer picture of our discussion. Now, all ladder diagrams must consist of certain points. So you have a ladder I want to discuss the ladder diagram, and then I look into the symbols, and then we'll end it there, and then we'll start programming in the next class. So a ladder diagram is like an electrical schematic, but ladder diagrams use rails and rungs. Remember, it's called a ladder because typically a ladder looks like this. All right? But now, usually these are called rails. But these ones in here are called, rungs. Okay? The rails are typically used for power supply. So they supply the wires of the relay logic. Okay? Now, the rungs is where you connect to the components. And this is the case, this is where we put in the symbols. We'll see, I'll draw a proper one in a short while. Okay? So when you're implementing a ladder logic program in a PLC, there are 7 basic parts of a ladder diagram that we must all know. The 7 basic parts. And these are the parts that I want to look at. And then we look at the symbols, and then we end our class. So let me just call them the 7 critical parts of a ladder diagram. Remember, this is like trying to see, whenever we were doing C, we were like, how do you initialize, so these are some of the areas we are also looking at to see how we can come up with a proper ladder diagram. The 7 critical parts. Number 1 are the rails. So all your ladder diagrams must have rails. All your ladder diagrams must have rungs. Very important. All your ladder diagrams must have inputs. Please note, every time you draw a ladder diagram, they must have these components. They must have outputs. So you cannot draw a ladder diagram without an input, and you cannot draw a ladder diagram without an output. All ladder diagrams must also have the logic expressions, which are the symbols. Okay? All ladder diagrams, very, very important. This is where almost 50% of the students forget and make mistakes. They must have an address notation. Okay? Or tag names. Students forget this a lot, and it costs them a great deal. The other one, the most important part of a ladder diagram, but the least considered by students, and yet it is the most important, is all ladder diagrams must have comments. You must comment on your ladder diagram to show us exactly what that ladder diagram does. You cannot assume that once you have dragged and dropped your symbols and your ladder diagram is in place, that the reader will automatically understand the function of that ladder diagram. You cannot assume that. Of course, somebody like me, if I read it, I would understand because I interact with it a lot. But anyone else reading it needs to understand. And so the best way to do that is to ensure that your ladder diagram has comments. Now, typically, just like we write our lines of code in the text-based code, I know those text-based usually have, you put your comments on the side of maybe each line of code. But in our ladder diagrams, we usually see that if you try and do that, if you try and write comments next to the ladder diagram, it makes it look very congested. So typically our comments are written just after the ladder diagram. I'll give you examples later, okay? Just after the ladder diagram. So the comments are usually explaining exactly what each line of your ladder diagram represents, or what each rung does. That's what we mean. So please remember that the rails are the two vertical lines of your ladder diagram. Okay? And in relay logic, in ladder diagram or in ladder logic, they simply are representative of the power supply. So one side would be 0 volts or the ground, and the other one would be 24 volts DC or 220 volts AC. So this is where power flows from. Okay? Then you've got your rungs, which are the horizontal lines. So the horizontal lines that connect the rails. Okay? So they're also just like wires. Like we have wires that are usually connecting components in a electric circuit. Then you've got your inputs. And we're going to discuss the type of inputs that exist in ladder diagrams. You've got your outputs, and then you've got the logic expression, which is simply the combination of what the input and output does. Then you've got your address notation, very important. You cannot draw symbols and without tagging them with names, and because this is software. So every symbol because every symbol stands for either an input or an output. Because they are logic based, they are simply memory locations. They are addressed. Those logic is either high or a low. That logic needs to be stored in a memory location. That memory location is only identified by its address. So you must tell me, or you must design as an engineer, a ladder diagram that consists of inputs and outputs. Those inputs and outputs are understood as memory locations because those memory locations hold a logic. The logic could be high or low, on or off, cold or hot. Whatever logic it is, they are put or they're stored in an address somewhere, a memory location. And of course, the comments. Extremely important part of the ladder diagram are the comments. And the comments are usually displayed. If your ladder diagram is not huge, you can put them at the start of each rank. But like I've told you, usually it looks very tedious and congested. So the best way is to describe you put your comments as an expression below the ladder diagram, where you simply are illustrating what happens in the first rank, what happens in the second rank, because it makes it easier for the reader to follow exactly what happens. So let me give you an example of a typical ladder diagram. This is just an example of a ladder diagram. We've said all ladder diagrams, and we're going to see if all these 7 components exist. All ladder diagrams must have the 2 vertical lines. Those vertical lines are called the rails. So this is rail. This is also another rail. Okay, very important. All ladder diagrams must consist of rungs. Those rungs connect inputs and outputs. So for example, let me just draw a typical ladder diagram. Notice I've used symbols here that I have not explained, but we are going to look at them. Okay, you could have another one, for example, like this. Let me use a normally closed contact. Of course, the output. Okay, so this could be rung number 2. So you can see how all the components, I've made sure that all the components exist in my ladder diagram. So this is rung 3. But now it is also very important for us. 1. So here I could put a tag. So you have an address. You put an address here. Okay. We'll look at how you do the addressing. Even here, it needs to have an address. Okay. It's a memory location. It's how the processor, while running through the scan cycle, how does the processor know, go to this address fetch this instruction, execute it, and then update this address. So the processor needs to know the location of each logic. So how does it know? Through the address. Okay. And I think because you did addressing in, I don't know whether we did the 8085 microprocessor. It's some lab we used to do, I don't know, in third year or something like that, or second year, where you actually learn how to do the addressing, where you go pick memory, an instruction. That instruction is stored in a certain memory location. Then you execute it, which again, the execution is done in another memory location. Then, you know, you store and maybe again, that exists in a different memory location. So each of these must have an address. We'll look at how we do the addressing later. That's not important now. Now we are simply just learning. So all this must have an address, okay? Now, the other thing that we're talking about is the comments. So sometimes, if you're using a software in the lab, you can put comments here. So I can write a comment here. Okay? Then for the second one, for the second rung, I can write a comment. So you see that we usually write a comment on top of each rung. Okay, so this is comment 1, this is comment 2, and then let's see, this is the third rung. So here you can also write your comment 3. Okay, but when you're drawing this and for use in class and for exam cases, it is usually very tedious to write comments because the comments can also be lengthy. And so when you put them within the ladder diagram, it consumes a lot of space. So we usually say you can write the comment here on the side like this. Put your comments there. Put your comment there, put your comment. But if your ladder diagram is also large that you don't have space on the sides, you can write your comments here. You can write your comment number 1 there. Okay, so this is comment 1. Then you come and write your comment 2 here. Okay, then you come and write your comment 3 here. So I'll repeat. In the lab, when you're actually interacting with ladder diagrams, there is usually enough space, and usually it can even prompt you to put a comment somewhere there. Okay, so you cannot write your comment elsewhere apart from at the top of each rung, you can put a comment. In class, for our own purposes, if we know that these spaces could be small, we can write our comments on the side, just like we do with text-based programs. But from my experience, usually that also doesn't help much because of space. So that's why we say, for space reasons, you can put your comments right at the bottom of your ladder diagram. But you have to comment for each rung. That means you have to tell us, what does rung 1 do? What does rung 2 do? What does rung 3 do? And remember, I will try as much as possible to do as many examples with you for real life or real world applications so that you understand exactly what I'm talking about. Okay. Now, I have used one thing that I have not mentioned is this part of the ladder diagram. The first half of the ladder diagram is known as the inputs and logic expressions. We'll do those logic expressions, input and logic expressions part. All ladder diagrams, the first half, the first left is for inputs and logic expressions. The right side of the ladder diagram is restricted for outputs only. Okay, that's also important for us to note that you cannot put outputs on the left side of the ladder diagram, just like you cannot put inputs on the right side of the ladder diagram. The left side is for inputs and logic expressions. The right side is for outputs. So all outputs must appear on the right and all inputs must appear on the left. That's a rule. Again, I will give you the 9 rules of constructing a ladder diagram later. Very, very important rules. Okay. And in the next class, we'll be looking at now the real logic for each of the devices that we have, or each of the symbols that we have in a ladder diagram. We'll do that on Wednesday. What I want to do now before the class ends in the next 20 minutes is, or less, is to look at the symbols, because I have drawn this, but we might not really understand what these symbols are. So this ladder, the ladder logic symbols. It's important I discuss this with you. We'll go into great depths in the next class, what each symbol does. Today, we just want to mention them, and then in the next class, we'll see the actual logic of these symbols. So symbols are the components. You know, like in electric circuits, you have, source, you have a resistor, you have a capacitor, you have an inductor, and so forth. Okay? In ladder logic, these are symbols. Okay? The components are symbols. So in the ladder logic symbols are the fundamental programming components that we use in ladder diagrams. They are these symbols that I've drawn within the ranks. Those symbols, very, very critical. Without them, then there's no ladder diagram. Okay? Now, we can use these ladder symbols either individually or as a combination in order to create a logic instruction. We'll look at that in the next class. That when you combine this symbol and this symbol and this symbol, you have created what is called a logic instruction. The logic instructions come from the input. Then the output is updated accordingly based on the logic instructions. That's why I told you the first left side of the ladder diagram is inputs and logic expressions. The inputs are the symbols. They stand for something in terms of logic. They stand for something. When you combine them together, they create a logic expression. We'll look at those expressions in the next class. So these symbols are created for logic operations, and we know the logic operations that exist. The logic operations are the operations of OR, AND, NOT, XOR, those logic operations. However, with time, those operations have also included higher level functions. So we not only achieve logic operations with these symbols, we also achieve the logic functions. I hope we know the difference now. We are final year students. Logic operations are the OR, AND, XOR, and so forth and so on. The logic functions are things like counters, timers, the math, subtraction and stuff like that. You have things like comparisons, comparators, comparisons, and stuff like that. You have PID loops, data manipulation, data conversion. We look at those are logic functions, but the logic operations are the basic operations of OR, AND, NAND, NOR, and so on and so forth. Okay? So quickly looking at the symbols. The most common symbol is known as the normally open contact, simply abbreviated NO. That contact always looks like this. Now, this is where I told you different manufacturers can bring a different symbol, but they are more or less exactly just like that. A manufacturer can decide that sisi yetu itakuwa inakaa hivi. So you see, it's just the symbol that looks a little different. The operation is the same, okay? So it doesn't matter. But the most common symbol is, as I've indicated there, a normally open contact. Remember, this is a symbol, but its work is to transfer logic from its input to its output. So for example, the normally open contact, it's like an open switch, okay? Meaning that the condition here is that whenever, if the condition is true, so if any condition is true, then the contact is closed and the output logic will flow. If a condition is false, then the contact is open and the output logic flow is blocked. We'll look at this in the next class. I don't want to look at the logic aspect right now because it will confuse you. I'll look at the logic, but this is like an open switch. So this stands for true. And when you activate it, it's simply open. So at this point, it's called normally open because in a true condition, it is open. When you activate it, it now closes. I hope that is clear. In its normal condition, it is open. It's like a switch. But when you activate it, then it now closes. So the operation will be in the next class. Let's look at some of the common uses where we use this. We use this type of logic when we are using things like the start push button. Think of the start push button. In a typical environment, the button is open. When you press that start push button, it completes the circuit and then now it allows current to flow. But in this case, it's logic that is flowing, not current. So a start push button is represented using a normally open contact because typically a start push button is open, meaning it is not allowing current to flow. But the moment you press it, it completes the circuit and current flows. So in ladder logic, we say a normally open contact is usually open in its normal condition. But when it is activated, meaning when you supply it with energy, then it simply closes, meaning logic flows through. So for you to pass logic through this contact, you need to activate it. Then logic will now pass through. So you have selector switches. Now, these are field devices that could be connected to this normally open contact. So remember, this is the logic. This is software. So so these are the field devices that can be represented using a normally open contact. So it could be a start push button or a selector switch. You remember the selector switches are those ones where you have to select. Maybe the first one is on, the next one is off, then the third one you put on and stuff like that. It could also be some digital instruments. I don't want to get into that, but that's the normally open contact. The next one that operates in the opposite logic is known as the normally closed contact, abbreviated NC. Okay, so this one usually looks like this. You put that in between. Some books, like I told you, will have theirs looking like that. Okay, but still it's the same. The principle is the same. So for the normally closed contact, meaning in its normal condition, it is closed, meaning at this stage, it is passing logic because the circuit is complete, the logic circuit. So if the condition is true, then the contact is open and the output logic is blocked. Meaning in this normal condition, it is allowing logic to pass through because you see, we have a closed operation here. So the normal condition is that logic is passing through. But when you activate this, or when you close it, let me just say, when you activate this contact, what happens is it opens and therefore it blocks the logic. So it is the exact opposite of the normally open contact. The normally open contact is open. When you activate it, it closes and then logic will flow through. The normally closed contact is already closed, so logic is flowing through in its normal condition. When you activate it, it now opens and then it blocks the logic. Now, activation, for those of you who've interacted with softwares, is that whenever you activate a normally open contact, it will turn green. Most of the softwares you will see now it changes to this. So this is off, and then this is on or activated. Off meaning there's 0 volts supplied. Here it is now your 24 volts DC or whatever has been supplied. So when it is activated, this turns green. When it turns green, it simply means that now it is allowing logic to pass through. Because it cannot be this, otherwise it would be normally closed contact. So yes, when it turns green, we understand it as closed. The symbol is the same, but when it turns green, when it is activated, it is now closed, meaning it allows logic to pass through. In its normal state, it is probably black. In its normal state, it is black, meaning logic is not flowing through. When you give it some energy, then it now turns green, meaning it is now allowing logic to pass through. The same way with the normally closed contact. When this normally closed contact is left, it's still black in color. Okay, I don't have black here, but it's still black in color. I'm talking about when you're now viewing it on the screen, on the software, you will see that it is black and it is allowing logic to pass through. But when you activate it, it turns green like that. When it turns green, the understanding is that it is now open. It is now blocking logic from passing through. So that's very, very important. Meaning the output here could be, let's say the output here should be 0 because it's normally open. The moment it's activated, the output now changes to 1. So it's allowing logic to pass through. This one, the output is just 1 because it's normally closed. But when you activate it, when it turns green, that logic turns back to 0. We'll look at this logic later in class. So this is usually called a NOT gate. Okay, this is the equivalent of a NOT gate that you studied in 3rd year digital electronics. Good. So now let me quickly look at the other main symbols that exist. Remember, I had introduced both the normally open contact and the normally closed contact. The other one is the output. You can see the right-hand side. So the output is also a very typical, a very, very common symbol that we use in let me just call it the output. Some people call it, it's called the output coil. So the output coil is represented as that. Some books, like I told you, will represent it with an O, but it's the same thing. It's an output. This is just the choice of notation by different manufacturers, but what it does remains the same. So the output is now what stores the output of the logic operation. So what we say is that if you leave it like this, it is not activated, then the output is 0. But when it turns green, when it's energized, when the output is energized, it turns on. Okay? But that is based on what the input was. So the condition of the output is that it will give you a result based on what the input condition was. Okay? So if the input condition is true, then the output becomes true. If the input condition is false, then the output becomes false. Okay? So this guy is like, if you give it a 0, that is what it will provide at the output. If you give it a 1, that is what it will provide at the output. Okay? But remember, those logic instructions emanate from, or those logic expressions emanate from the inputs. That is what will determine what the output provides. Okay? So the output coil, like I mentioned, could represent, or as a field device, it could be the motors, it could be the actuators, it could be the indication lamps. We'll look at those. It could be a warning siren, and so on and so forth. So that's another important symbol. Now, the other symbols that we'll encounter again later, once we are well conversant with these, are other very specialized type of symbols. One is known as the positive transition sensing contact. Positive transition sensing contact. It's not commonly used, we use it only when we are applying certain very specific instructions. And so the difference is it's usually just denoted by P right there. Then the other one, of course, is the negative transition sensing contact. Again, rarely used, but still it is used. So it's important that I indicate that we can use this type of symbols later for other purposes. The other one that's also very common that I need to mention is what we call the negated output coil. So we know that the output coil is this, meaning the output coil is just what I usually say is a follower. You give it a 0, it gives you a 0. You give it a 1, it gives you a 1. Okay? But the negated, remember, this is now a negated output coil. So the negated output coil, you will see it in some books. So it's denoted that. That's a negated coil, meaning you give it a 0, it will now give you a 1. You give it a 1, it will give you a 0. Okay? But it's an output. There's a reason why sometimes this negated coil is very important, certain applications. I'll give you an example later. We'll do an example where you need to use the negated coil. Okay? So it simply means that in your ladder diagram, you could have this, and then the next one is negated like that. Okay? So that exists. So we've talked about the negated. The other one, again, I've told you the most common ones are the normally open contact, the normally closed contact, and the output coil. But for certain specific applications and design, we need a positive transition sensing contact, a negative transition sensing contact, and a negated output coil. For cases of latching, we have a set latch coil. We'll do latching, and we have a reset latch coil. Okay? We'll see what latching is and what that means. So the set latch coil is simply S there. The reset latch coil is this. Okay? We also have a positive transition sensing coil, not contact. Remember, these ones were positive transition sensing contact and a negative transition sensing contact. We also have a positive transition sensing coil, P, and then we have a negative transition sensing coil with an N. Okay, not contacts, this time coils. So please see how many coils we have. You've got the normal output coil, then you've got the negated output coil, then you've got the set latch coil, you've got the reset latch coil, you've got the positive transition sensing coil and the negative transition sensing coil. Several, and all these are output coils so that they appear on the right side of the ladder diagrams. However, the positive transition sensing contact, the negative transition sensing contact, the normal closed contact, and the normally open contact appear on the left side because they provide you with the logic expression or the logic function. So these are the major, there are several other ladder symbols, by the way, several others. We've not even included timers, we've not included counters, but those ones are special ones. We'll talk about them in the second phase of our study. For now, we need to understand the basic ones and how they operate. So these are the symbols that we use in our typical ladder diagram construction. In the next class, we look at how each of these is affected by logic and how we can generate logic expressions from these symbols and see how those logic expressions can affect the output based on how we arrange each of these inputs, whether they are these contacts normally open or normally closed, or the positive transition or negative transition, as well as see how the output is also affected. But please remember, what we are talking about here is the transfer of logic, not transfer of current. So if you're transferring current, if we say that the contact is on, it means it's activated, meaning it is allowing logic either to pass through or it is blocking logic. Because when you activate a contact, it can either allow a logic to pass through based on what contact that is, or it can block logic from passing through. And when we say passing through, meaning allowing it to pass through to go to the coil or to go to the output. So we'll do quite a number of examples and even draw the truth table and look at some of the logic expressions that we have. For example, how can we express an XOR gate or a NAND gate or even an OR gate using PLCs, such that now we are able to control what is at the output based on the inputs that we provide. You know how an OR gate operates. So how can you control, provide that kind of logic operation using PLCs? We'll look at those. Those are the basic ones. And then we'll graduate to more complex applications and how we can achieve them. So I want to end my class here, ladies and gentlemen, unless there are any questions, please, because I have another class in 10 minutes, so I need a break. If there are any questions, you may ask. Otherwise, our class ends here. Swali? Yes, for sure.
Yes, when you introduce the PLC architecture and kind of drew a red boundary around the blocks, there's a statement you made I did not quite get it, where I think something like PLC is defined by the software, not the hardware.
Oh, yeah. So when I drew that, sorry for the scrolling, I have to. What I said is it's usually very confusing for people who are starting off to separate what the PLC is from what the hardware devices are. The hardware devices are those devices that we physically operate. If I push a button, that's a hardware device. If I select a switch, or if there's a solenoid valve, those are hardware devices. If the motor starts running, that's a hardware device. But what controls that motor is the software aspect, in this case, the PLC. So the boundary that I drew in red here are the PLC components. The PLC components. Now, PLC is a software, it's a program, okay? So that we understand that those PLC structure consists of input and output modules, it consists of a power supply, it consists of a CPU, it consists of a programming device. Now, we can see the power supply that's providing power to the PLC. We can see the CPU because it's an actual device that we can see. The programming device, we know we can program using our computers and stuff like that. What I was trying to emphasize is this. The input module of the PLC is not a physical device. The same way, the output module of a PLC is also not a physical device. The point is, whenever we are operating a device, or whenever we see the output of an operation, or whatever application it is, we see the physical ones. But whatever is operating that is a program. So the interface between whenever I push a button, so let me say I want to push a button so that the light goes on. Whenever I push a button, it is a physical device. But whenever we use PLCs to control that light, I push the button, which is a physical device. The command goes to the input interface, the input module, which is now a logic device. So Mimi, I pressed the switch. So the switch is on the wall, or the push button is on the wall. I've pressed it. That has activated an electrical energy. That energy is being transferred to the rails. The rails will activate the input module. The input module is now a normally open contact or a normally closed contact, because it is taking that electrical signal that I pressed on the push button, converting it into a logic, a 0 or a 1, a true or a false. Then it is pushing that to the CPU to operate. So the CPU is acting on logic. The power supply is acting on logic. The programming device is on logic. The output module is on logic. But when it gets to the output field device, the load devices, that logic is transferred back into an electrical actuation. So if it was a motor, it will start rotating. If it was a lamp, it will turn on. So what I was emphasizing is whatever you see on the red block, the big red block, are logic-based operations. But whatever you see on the left and the right after the blocks are electrically based operations or electronically based operations. They could be an actuation or a sensing device, but whatever happens within the big block is done in a logic manner, a 0 or a 1. That is why I was insisting that that is a software element. But whatever happens outside the big block are hardware operations. That is why I push a button, that's a physical operation, but it will be converted into a logic operation by the input module. So the input module will not see 5 volts or 24 volts or whatever. It will see a logic high or a logic low, then transfer that to the CPU and so on. And so whatever happens in the big block is what we are calling the software aspect. Whatever happens outside that is the hardware component. I don't know whether that is clear to you guys.
Yes, thank you.
All right. Any other question before we close? Let me stop sharing to see if there are any hands. I don't see any other hands. All right. Thank you so much, ladies and gentlemen. I think we'll meet on Wednesday for the 1 hour and see how those logic operations work for each of the symbols that we have discussed today. All right. Have a good day. And